going to model a indeterminate beam. As you see in the handout, an indeterminate beam of length like 8 meter with the help of SAP. And here we go. This is a SAP 2000, and at the start of it is giving you tips, doesn't matter. Okay, now the thing is we are given a beam of length 8 meter, loaded with a uniformly distributed load of 20 kilonewton per meter, with a section properties like the material is steel. You can see the section modulus is 200 GPa, and the cross section is a square of 800 mm by 800 mm. So here we go. The first, we need to make the unit very correct. That is, uh, you can go with any units. Like the first one is for force, second one is for displacement, and the third one is for temperature. And since we are not anyhow doing this to temperature, it's not important, this C and F, Fahrenheit and Celsius. The most important is this force and length. So I would like to go with kilonewton mm. Celsius and Fahrenheit doesn't matter. Okay. And the thing is, now you need to open a new file, new model, and there are different kind of template popping out. Some are blank, grid, beam, and the question you may ask is, it's a beam, we can go with beam. Yeah, that's correct, but the thing is, this is the most general one, the grid only. If you go with this, you can make any other, even if the template is not in the SAP. So I personally recommend you to go with grid only, because believe me, it's very important, and it's very general. And if you know how to do anything with grid only, then it doesn't matter either the SAP provide you template or not. So I would like to go with grid only. Here we go. Now what the screen is showing us is a coordinate system. There are two kind of coordinate system: Cartesian coordinate, cylindrical coordinate. Since we are not dealing with anything that is round, curved, circular, we are not going with cylindrical, we are going with the Cartesian. And the thing is, like, you can make it, you can feel it, like our beam is going in X direction and rest other direction are not important to us. So what we need to do is we need to make a two grid line that are at A and that is on B. Okay, and the thing is, and the distance between these two grid line is 8 meter. So number of grid lines here, it is 2. We don't bother with these two. And the number of sorry, the grid spacing is how much? Its default value is like 6,000. And one thing keep in mind, this is in mm, so you should put it like 8,000. Here we go. Other doesn't matter. Here we go. The screen, there are two screens. Oh, this is for, you can put anything on this screen like 3D, XY, XG, YG, and this is, you can name it. But what people generally do is put some 2D view on this and put 3D view on this, so that they can grasp the big picture of the beam. And now the first thing first, what we should do is, the most important thing is, this is A point of the beam. If you make it small, this is the A point of the beam. But go to options, 3D. Okay, the important thing is 3D view up direction. The SAP has a inbuilt for G, and you, it's better you get accustomed with this, because the thing is SAP always uses G as the 3D view of direction in a default way. So it's fine. So what we need to do is, this is not the plane, this is not the plane we want to look for. Actually the plane is XZ, this is the plane, this is now 800 mm. Okay, now sometime you need to change this grid, like the standard template is giving you for equidistance and grid distance. uh, it always say like between two grids you have to choose either 600 or 6000, and it always give you equi-space. But the thing is, you can go here and change edit grid data, you can go to modify source system, you can go here and you can change. We don't want to change this because this is what we require. We may do some experiment on this, like uh, in y direction. We don't see y direction here, so let's go for g direction. In g direction there are how many grids? 1 2 3 4 5 5. 1 2 3 4 5, and the distance between each line is how much? 3000 mm. And if you use the standard template for that one, it's always going to be equally spaced. But for example, if you need it 4000, you can go for it 4000, and you can go for it like 5000. Okay, and it will get changed just to make you understand, but it doesn't matter in our case. Okay, if you do, okay, now look at this, and these are not equidistant now, so you need this feature often, because in the truss or other structure this doesn't happen always. So now we need to go to view, sorry, we need to go to define and define the material. So our material is a steel with 200 GPa, so we might go to add new material, and we might want to write steel, that is our name, steel. And you better notice this, because this is kilonewton mm. This is almost close. Okay, this is like 199.948 GPa, that is very precise, the SAP gives you, but our is 200 GPa, and GPa is kilonewton per mm square, so I can use like 200. There are other properties like Poisson's ratio, coefficient of thermal expansion, shear modulus. They don't bother us in this case, because we are not using this parameter anyway. But the thing is, you might be interested. There is a special relationship between E, Poisson's ratio, U, and shear modulus G. So you change U like 0.25, you will get the section modulus different. This is now 76.92. Now you go to here, it is 80. Okay, and you change it into zero point 0.5, which you don't want to do, because there is a zero point 0.4. You go here, it's changing. So you can change this. This is a default. You can change this, and by the relationship between G, U, and E, G gets automatically changed. So this is this, and what we are bothering is, just keep it as it is. So what we need is only this. So other parameter, or we don't have to either go to advanced property. We might need it in future, but not now. Okay. Now we have a steel. Okay. Now we define the material. Now we need to define the geometry. That is, the steel section is 800 by 800. Okay, here we go. Section properties, frame section, a new property. Yeah, there are a lot of templates. Look at this, is I a W. In US it's called W, in Europe it's called I. There is a little difference. Channel section, G, angle, a lot of stuff. But what we need was solid square, and there is nothing like this. Now the thing is, you can also import from the other software, or you can make it by yourself. Like go to other. Here is you need to import or make it. You want to do it, but here is something else. This is don't want to do. Now a new property. You might want to go to section designer. Here it is. We want to make it a square, and what we need to do is, this is not for 1000 psi, this is our steel. Go to section designer, you go with this. Here is the draw solid shapes, okay, and you go here. There are various solid shapes like pie, this is arc pie, this is circle. You go with this and you click here. You get a default square that is 500 mm by 500 mm, but the thing is our dimension is not that, so we need to change it into, like, this is 500 by 500, we need to change it into 800 by 800. Okay, now you need to change it into what you call square, our square, and this is not 4000 psi, this is steel. We need to look it here. Okay, here we go. Now it's done. Now this section is 800 by 800. If you want to see its property, you can go to display, so section property. Here the area is 640,000. There are other properties too, but we are not interested. Whatever it gives, it is fine, because SAP is able to do that. We need I to find the deflection. This is IYY, this is IJG, this is, sorry, this is IYY, this is IGG, this is IXX, and this is IXY. This IXY 0 because it is symmetrical about both axes, and you might know that. And there are a lot of other properties, advanced properties. We don't need to bother with these. We just need these first few columns and they are fine. The area is fine. Other properties, it calculated by using like uh, breadth into height power 3 divided by 12. It has done that. That's fine. SAP is doing it by own. We don't need to give this to them, so it's okay. The unit is also okay. Axis angle, it doesn't matter. Okay, so this is our section. We are done with this. We are done with this. We are done with this. Now what we did was, we defined the section, we defined the material, we know the length of the beam. Now we need to fix a node here. This node is a fixed node. This is also fixed. You choose this, you choose the node. Okay, sorry, this is, now since the memory is not made, now you go here. Our section is square, that is fine. Sometimes it goes to non. It is a continuous structure. This is very much important. If you are dealing with truss, you should go to pin. If you are dealing with beam or frame, you should go to continuous. Rest other is fine. You go here, that is fine. You go from here, and this is your structure. Now this is your beam, this is a section. Okay, and what about this? This is 800 by 800 mm in dimension. This is a steel. It consists everything. Now the thing is, you need to put a node here, whatever node the handout is giving. This is also fixed, this is also fixed, so you might want to put this way. First select the nodes, go to assign, go to joint loads. Now you want to go to joint, then go to restraint. Okay, here is a shortcut for it. This is a fix, this is a hinge, this is a roller, this is a pin. Look, in pin everything is released. This is a free node, and you might want to go here. If you select this, all things are restrained, so you click this, you will get a fixed joint both A and B. That's all. Now what do we need to do? We did everything, but we haven't put the load yet. So what we need to do is define. Now we need to go to load pattern, and we need to put it our load. Okay, so I might want to put it some unique name so that I can know which system to run. Like, let's put it example. Okay, that's the name of the load pattern. That doesn't matter. Put it anything. But this is important. This is a live load, and self-weight multiplier is also this is also very important, because if we put 1, then it will be live load plus tail load. If we put 2 here, it will be live load, example load plus 2 times tail load. So it's fine, we go with 0. Then add new load pattern. Here we go with example live load, that is with a self weight multiplier of 0. That's fine. It's okay. Okay. Now we have a load pattern. Now what we do is, if we wish to put load on the nodes, then we select the node like this. But since we wish to put load on a member, we might want to do like this. Select the section, and what we need to do is assign, and there is a frame load, and we might want to go with distributed. So what is the name of the load? Our load name was example, and we want to put the force in the global, in gravity direction, everything is fine, and the load is 20. Now you might find this reasonable, but the thing is, if you do this, you are in a problem. The load is 20 kilonewton per meter by equation by system, but this is 20 kilonewton per mm, because the unit is mm. So you might want to change this into kilonewton meter. Okay, and it is automatically changing, so you might want to put this 20. Now it is 20 kilonewton per meter. Get me? Now everything looks fine. You can go. Okay, now here's the load. But why it is showing 0.02? It's because here it is kilonewton mm. So you might want to change this to kilonewton meter. Where is kilonewton meter? Okay, if I click this, this must be 20. Okay, here we go. Now we put everything. The section is okay, the load is okay, the node is okay, the material is okay. Now what we need to do is just run the analysis, and you will get the solution. So run it, and we don't want to, okay, we don't want to run this one. This is do not run. We don't want to run this one. Do not run. We want to run this. So run now, and it will ask you to save it, and it's a, sorry, what did I, beam, and we want to save it in a desktop. Now it's saved. Now it's running the model. Okay, the model is now ready. Now there are different kind of thing you want to look like. First, we might be interested to look in an axial force diagram. So here is a display, and you can say, so force and stress go to axial force is not in the node. Axial force diagram is not in the node, it is in the member. So go to this, you click here, it is already axial force diagram. The load is also okay, example, and here we go. It's coming 0. It's, you might say it's coming 0. Why? Because there is no axial force. Now let's go to display, go to show force, go to frame. Now let's go to shear. Okay, now it must be coming. Now you can show field diagram, you can show value. Okay, show value. Okay, now this is something called, what do you call this? Is shear force diagram. It's a negative here, red one, minus 80, going linearly to 80. Okay, now the next thing is display, so forces, frame and cable. You want to see the moment. Okay, here we go. What's wrong? Oh, sorry, we put moment 2 2. We should do it with moment 3 3. Sorry. Payment cable moment 3 3. That's because MZZ, not MYY. We need to, okay, so values. Okay, this is the moment diagram. Or you can go with this one also. So forces, this is the same thing. You want to go to field diagram, okay, it will show you like this. But this is, okay, I want to ban it. This, uh, I think this is not so good. I think this one is better because it will show you the values. Okay, this is minus 106 and this is same minus 106. This is somewhat 53. That's all. And what about reactions? You can also go with reactions. Like here, it is just for force. Okay, you can go with display. You can, so forces, reactions are at joints. So example, okay, now this is the reaction. Okay, and it doesn't show moment here. You need to go to display table. Okay, this is very important. You need to go to this one. You need to go to displacement. You need to go to reactions, and this is joint output. In the element output, okay, element output is also fine. Now you want to see this. Okay, this is something element force. Look at this is shear force. This is axial force is 0 everywhere. Okay, this is shear force. Okay, minus 80, minus 70, it is going, and it's minus 80 to 80 at the each point. You can go here, whatever you choose. Like you can joint reaction. Joint reaction is okay. Look at node 1, it's 80 kilonewton. At node 2, it's 80 kilonewton. At node 1, it is minus 106 kilonewton meter. That's all. You can go to element force. We already did it. You can go to anywhere you want. So, and the important thing is you can change this file and import this to actual, export current file to anything actual. Okay, the actual is popping out here. This is the actual file. This is something you don't want. It doesn't matter. This is something. Now you can delete some unwanted things from here and put some worthy data. Like you are interested in 0 and 8. Yeah, but the thing is the shear force 8 is minus 80 to 80, so it's showing that way. Okay, at 0.5 it is minus 70, at 1 it is minus 60, at 1 point it's showing, at 4 it's 0. That's fine. That's all. And element station is given here, and you might want to save it. It doesn't matter. You can save it anyhow. That's all. This is how we can do a beam with the help of SAP. Okay, so from this example you can learn many things, and hope you enjoy learning. Good luck.